Hello, good morning, everyone. I'm honored to be a part of this very knowledgeful session, and we have it's good to hear directly from uh, HOD Electrical of IIT Kharagpur and Mr. Das, who has such a great experience. And it's very heartening and pleasant to see that a forum like employee welfare is, so much keen on learning capability building of its employees. We normally such kind of forums are, engaged in employee welfare. So it's very, uh, I'm very happy to see that. So my topic for the day is energy storage. The way we see as a developer, NTPC is a developer. We are developing solar plants, wind plants, and now also going to energy storage. So some of this has I think already been covered by Das sir. So as we all know that India's green energy success story has been quite successful, and from 15 rupees, 18 rupees tariff of solar, we have gone to around 2 rupees tariff. There were times when government had to force installation of solar plants, and now it is the choice of the customer. And going ahead on that path, our Prime Minister has declared goals for COP26 that will reduce 45% of our emissions by 2030, will be net zero carbon by 2070, and 50% of our energy will come from renewable sources by 2030. And to do that, we have kept a target of 500 gigawatt of RE by 2030. So, but with that, will there'll be a lot of challenges will also come into the grid, because as Das sir has already said that because of the variable nature of the sources, generation sources that are there. So wind is very it's very unpredictable in nature across the day, across seasons, and there are minute to minute variations. So integrating such kind of resource into the grid, it becomes very challenging for the grid operator to stabilize the grid. And solar generation also, on normal days, it is sort of a stable generation. It is a predictive generation. You can predict to some extent that it is going to follow a certain kind of trajectory. But on cloudy days, as sir was talking about Andaman, so there we have some issues like that when there is cloudy movement. So it also becomes very unpredictable. And the on top of that, the demand timing of the load is much different from the supply timing. So supply, you can see that it happens mainly during the mid of the day, whereas the demand is on the morning of the day as well as on the evening of the day. So till now we could add whatever capacity we have added, because there was quite good amount of base load from thermal and from nuclear and from hydro plants. So we could use this renewable energy without doing much into energy storage. But now as we go ahead, this won't be the case anymore. So we'll have to put energy storage into the grid. So just briefly, uh, uh, two main uses of energy storage: peak shaving. So there are two peaks, morning peak and evening peak from the load side. But for the generation side, we have the afternoon peak. So this can be shifted. We can charge the batteries during the daytime, and we can discharge during the evening and morning time. Then PV smoothing. So if there are fluctuations, we can have a smaller scale of battery with less in energy density, but more on the power capacity. So that can be used to smoothen the curve. So with all these battery, not just battery storage, energy storage as a whole can serve lot of purposes on the grid. If you see from the bigger grid scale side, so they can provide flexibility and reliability and ensuring security of the grid. They can bridge the gap between the demand and supply. We can do peak shifting, peak shaving, ramp up control, frequency control. And sometimes we have to curtail the RE, renewable energy generation, which has zero marginal cost. So whenever you are curtailing the RE, you are actually making a loss to the country. So this problem can also be handled by the energy storage, and this will enable us to transition smoothly from this conventional based energy sources to renewable sources, and it will help us in maintaining our commitment to environment, and it will also help us in reducing the cycling of the thermal plants. So as of today, in recent years, a lot of cycling of thermal plants is being done. Plants which used to operate at 80%, 90% PLF a few years back are now operating at 60%, 70%. So there is underutilization of the thermal plant asset also, and frequent ramp up, ramp down is also affecting the life of the thermal plants. So with this, we can also address that. So just a outlook of the Indian power sector. This is a report by the CEA, wherein projections have been made for next 10 years. So if we take a scenario for around 2031, 32, uh, there's expected to be around 360 gigawatt capacity requirement, and in energy terms, if we talk, it will be like 24 lakhs million units that are going to be required around 2030. So if you work out in, in detail, and see what kind of storage and what kind of solar, wind, and all those things will be required to meet that demand. So it's predicted to be around that there is be peak load demand of 325 gigawatt, and to meet that we'll have to install around 775 gigawatt of total generation capacity. And with the in that solar is expected to be around 270 gigawatt, wind is expected to be around 120 gigawatt, and other sources. And to manage all these things, we'll need around 25 gigawatt of battery energy storage system, and with an approximate duration of 4 hours to 5 hours. So this is another projection by a group called ISA, which they are closely into, energy storage. So they have predicted a requirement of around 160 gigawatt hour by 2030. Of that, around 100 gigawatt maybe will be required for renewable integration, and for the discom side, it will be around 18 gigawatt hour, and for consume like commercial and industrial customers, large industrial customers, it will be around 26 gigawatt, and ancillary services, it will be around 5 gigawatt hour. So as we have seen that there are, multiple needs of wherein this energy storage has to address the requirement. So for and to address these requirements, there will be requirement of different solutions ranging from kilowatts to megawatts to in the range of gigawatts. So there will be solutions required in the range of, if we have to do integration, it will be around megawatt scale of 250 megawatt, 500 megawatt. If you have to do load shifting, then also around a megawatt scale. If you are doing ancillary services, maybe we require lesser capacity. So as of now, as we all know that there are a lot of options available in energy storage. Mechanical, we have pumped hydro, compressed air, flywheel, electrochemical, a lot of batteries like lead acid, lithium, sodium sulfur, zinc. Thermal energy storage is also there. Then maybe if we need a very short burst of energies, we can use supercapacitors. And then chemical storage, where you can use power to power, that's in fuel cells, or maybe power to gas, you can use green hydrogen and like that. So there are a lot of, plethora of technologies that are available, and each of these will have its own space because there are different requirements. So there'll never be one solution fits all condition, because and that is we are trying to show here. Like if you say a pumped hydro, so if the need of discharge is around in hours or days, and power requirement is around megawatt hours, so you will have solutions like pumped hydro, compressed air, or hydrogen fuel cell. Whereas if your requirement is very less, like in the range of kilowatts and seconds, then you can use supercapacitors. Then flow batteries can also help you give you long duration energy storage sources. So there will be a mix of solutions. So just I have covered one or two types of storage which are moved from, labs and notebooks to actually implementable solutions. So gravimetric storage is one of emerging technology which is certainly gaining commercialization. So these can be different types. I've just shown one type wherein you can lift the blocks from one altitude to higher altitude, uh, and then you can store the energy. So Energy Vault is one such company, and they have made a solution, I think prototype solution of around 20 megawatt hour or 80 megawatt hour, and we have signed an MOU also with them, and we are exploring how we can, integrate this gravity storage into long scale duration. Then compressed air, in the air is compressed uh, when we need to charge or store energy. That air is compressed and stored in underground tanks, and in that process the heat that is generated, that is removed, and that is, conserved. And then when there is a requirement, you release a compressed gas, and you drive the turbine through that, and you whatever heat you have saved, you have to put back the heat during that process. So these plants, if become commercial, then they can be very good use for grid storage point of view, because there the space is not a constraint. what we need is efficiency and life cycle. So they can give you around 5,000 to 20,000 cycles and a span of 25 to 40. So and this also I think they are just gaining commercialization in Israel. One company is Augment. So they have actually installed a demo system of 250 kilowatt and 1 megawatt hour. And pumped hydro has been there since eternal. And as we all know that there can be two reservoirs, upper reservoir, lower reservoir. So during charging we can transfer the water from lower reservoir to upper reservoir, and when we need power we can use the potential energy of water to generate electricity. So these are also from grid point of view very good solution for a long term energy storage, because their life is very long. They have 50 to 60 years of life, and the degradation or performance deterioration challenges are not there that are there with the electrochemical storage. And cycle life of around 20,000 to 50,000. And uh, we already have some pump storage, and lots of works is going on in Andhra. A lot of sites have been identified, but okay, we'll come to the challenge. But the challenges with pumped hydro is that capital intensive. You have to invest huge amount of money. So taking a decision of such amount of decision, it becomes difficult, and they have long execution time. So if I decide that I have to requirement of pumps of storage of certain gigawatt, and I start building a plant, I'll be able to get it only after 5 to 6 years. So that becomes a very challenging to maintain the grid with such kind of time, and there are environmental issues with that. Compressed air gravimetric, they are also modular in design. They can be installed quickly, but that manufacturing readiness is yet to come. So they are more on the prototype side, and commercially just starting to pick up, and efficiencies are low. So if the cost of energy is high, then these solutions become unviable. So a better option as of now is electrochemical storage, because they're technologically very proven, as sir has already talked about. There are a lot of technologies available, which can give you a lot of solutions. Commercially they are proven. They have smaller lead time. You can just quickly install. Like if I decide I have to put a plant, maybe in 6 months or 1 year of time, I can commission a battery energy storage plant. And they can have customizable solutions because of the different chemistries, and before the different inverters and BMS systems you can have for maybe long duration storage. You can have for ancillary services. So you can have different solutions. You can have from kilowatt hour range to megawatt or gigawatt hour scale, because the design is modular. So when it come to electrochemical chemistry, so some chemistries that are more popular are lithium ion, which can give you a cycle life of around 500 to 10,000 cycles depending on the sub chemistry that we are using, and they can have a life of 5 to 15 years. Sodium sulfur, which can give you a life of 5,000 to 20,000 cycles. Lead acid, it is lower on the sustainability side, so it can give you around 200 to 2,000 cycles. Flow batteries are also a new emerging setup, so they can also give you 5,000 plus and life of 25 years plus batteries. Yes. So just a basic of lithium ion cell, this anode cathode, and during discharging the lithium ions move from anode to cathode, and there is separator. So what are the USPs of lithium ion batteries? Why they are in so much force? Because they are high in energy density, that ranges from 100 to 325 watt hour per kgs. They have huge power density, 4,000 to 6,500 watt per kg. Cycle life is also good, 1,000 to 4,000, and round trip efficiency is very good. Other technologies might give you 70%, 60%. So they are compact in size. They have long service life. They can provide you fast charging, discharging rate, and they don't have memory effect, which affects the battery performance over years. uh, but there are also challenges, like sir had mentioned that battery safety in lithium ion is a huge challenge, because the charging, you cannot overcharge a lithium ion battery. If you do that, then there's going to be thermal runaway and it may explode. So battery management and safety of lithium ion batteries are very big concern. We have seen so many EV fires recently, that is affecting the image of the battery industry. and you cannot do deep discharge. So when we use battery lithium ion battery, so battery management system becomes a very critical part of the setup. So I've just mentioned some chemistries, lithium ion chemistry, that are in use. LFP, lithium iron phosphate. So these are based on the basis of the cathode material that we are using. So if we are using phosphate as a cathode material, then it becomes LFP. So it has high current rating and it can give you long cycle lives. Whereas if you are using nickel and manganese as cathode, uh, it becomes NMC. So and these are slowly taking over LFPs because of their higher specific energy density and thermal characteristics. Then LCO, which are mostly used in our consumer electronic batteries, where cobalt oxide is used as the anode, and LMO, where we use lithium manganese dioxide as cathode. So they have low internal resistance and good current handling, and they can provide higher thermal stability, which is less in LFP and NMC chemistry. But their cycle life and calendar life are less as compared to other chemistries. So you can see each chemistry has its own USP. It will go with a special kind of requirement. So there is another category, that's LTO, wherein in here in fact lithium titanate replaces the graphite as the anode, which is the default case in all other chemistries. So with this we get a very good amount of surface area on the anodes, which is around 100 square per meter. In normal other batteries it's around 3 square meters per gram. So that enables you to have very fast charging, and it gives you enhanced lifetime of the battery. Then there are solid state batteries. Solid state because there the electrolyte is also solid instead of being a molten state or gel state like in other batteries. And these are very futuristic, highly advanced, and these are going to be the next generation batteries, and they deliver very high performance and safety, but that comes at a cost and they are expensive to manufacture. And one disadvantage with them is also that their conductivity reduces at very low temperature, and there is concern of dendrite formation, which leads to short circuits. So we can see that different chemistries have different advantages, different specific energies, so they are suited for different applications. So if you move out from lithium, then some prevalent technologies are sodium sulfur. So in sodium sulfur batteries, you can say, are similar to lithium ion batteries, but here the movement of ion is not of lithium but rather of sodium. And one challenge with them is that they require high operating temperatures of around 270 degree to 350 degree Celsius. So we have to provide constant heating sources to operate these batteries. Then redox flow batteries, wherein you have two containers having electrolytes at different oxidation states, and that during the charging and discharging process, the electrolyte moves from one container to the other, from one oxidation state to the other. The capacity, or you can say the energy capacity, or megawatt hour, kilowatt hour of the battery, depends on the size of the container of the electrolyte, whereas the power capacity, or if we say in the kilowatt or megawatt, that depends on the uh, uh, PEM membrane, or the exchange where the plates where the exchange is happening. So we can say these are similar to fuel cells, but the disadvantage that there are a lot of mechanical parts, pumps and sensors, which affect the operation, operability and reliability. Then there are a lot of other chemistries under development: aluminum air, nickel manganese, metal air, zinc air, other metal air batteries, and lithium sulfur batteries. So we can see that different chemistries have different characteristics. Some are very energy dense, some are power dense, some have good round trip efficiency, some are lower in cost, and research and R&D is constantly underway in all of these technologies. And we have predicted, some organizations have predicted that this is going to be the future path of the research. So if you talk of cell cycle life and efficiency, so again different chemistries are placed very differently. So like LTO, if we see, it has a very high cycle life, and round trip efficiency is also very high. So if you are using long term project like 10 years, 15 years, 20 years, we can use such kind of batteries. But we have a short project of say 5 years, 10 years, then LMC, NMC, LFP batteries might be more useful because they have lesser cycle life, but their cost is also less. Then energy density wise, we can see volumetric energy density versus and gravimetric energy density. So LTO, LFP chemistries are in the range of 150 or 200 kilowatt hour, whereas if you go to other technologies like lithium sulfur or fuel cell, so their energy density is not so much, that is around the range of 700 watt hour per liter. So these are the projections. I think the cost of lithium ion batteries has come down drastically in last 7 to 8 years. Although last year there was some certain hiccups, but now again it seems to be coming down. So there are projections that it should come down to under $100 per kilowatt hour. So maybe then we can use more on the more of these in the commercial industry. So for batteries, there's always going to be two major use cases: EV and stationary storage. But EVs as of now have driven the technology industry, the commercial industries, because they have been at the forefront. So all of the research of the industry that has been now there is mainly driven by the EV market. But stationary storage has its a different requirement, because energy density, that is the requirement in EVs, that is not there in grid scale, because we have huge amount of land. Our concern is mainly on the cycle life. It should have a high cycle life, it should have high efficiency, so that the energy that we are putting in should not get lost. So it's like we are like even the Ministry of Power has acknowledged this, and we are coming up with a separate PLI scheme for batteries for stationary energy storage, because now that the PLI that has gone of 50 gigawatt hour, so that is mostly going for the EVs. So there is a shortage of supply for the stationary energy storage market. uh, and the battery supplies also, are mostly tied up with the EV manufacturers. So if you talk of stationary energy storage, the key drivers would be, we need long duration energy storage system, and systems which can deliver life beyond 25 years, because plants that solar plants or wind plants that we are building are normally modeled for 25 years. So if we are committing a solution, or if we are committing a bid, a certain price in a bid, wherein we are taking all components, solar, wind, and battery also. So if we have a solution which can sustain a life of 25 years, or if we can predict the cost of that solution for 25 years, then it becomes easy for a developer like us to model that cost and give a realistic tariff. So and the system, and we need a system with high round trip efficiency. So whenever we put energy in the battery and we take it out, so normally 20%, 30%, 15% of the energy is lost. So as a cost of this energy is going to increase, and if you are going to lose such kind of energy, then it's not going to be sustainable for us. So this is just a rough tariff analysis that was done internally during a presentation to ministry, uh, where it we have identified two major solutions for the energy storage in the years to come. In the next 5 to 6 years, the ministry has identified: one is the battery energy storage, and one is the pump storage. Other solutions are there, but because of the different commercial readiness and technology readiness, as of now these two solutions have been identified to take forward. So we can see that the cost of storage is very high, around 9 rupees or 10 rupees, as per the existing whatever tax duties and things are there. So if we the normally the cost of solar energy is around 2 rupees, 3 rupees, and if we put that into battery and take that out, so it comes around 13 rupees, 14 rupees. So that power is not sellable. So that is why we get seeing a lot of talks on battery energy storage, but things are not getting on the ground. So these things we need to address. Whereas pump storage has an advantage over here. The cost of storage around comes around 5 rupees or 6 rupees. So as of now, if we see, the price for pump storage is much ahead. And in fact, NTPC had floated a tender of around 3000 megawatt hour, that was technology and agnostic, when any energy storage technology could participate. So their entire capacity has gone to suppliers who are having pumped energy storage, because battery energy storage could not compete with pumped energy storage. So there are talks of reduction in custom duty, in interest subvention, and providing VGF. As sir had just told that the ministry has announced VGF for around for 4,000 megawatt hour of batteries in recent. So even with that, expected to come around 7 rupees or for battery storage and 4 rupees for pump storage. So that is a challenge for integration of energy storage to the grid. Policy side and regulatory side, government has been making consistent efforts to formalize the framework for the energy storage and to provide whatever enablers are required for this industry to go forward. So they have clearly clarified like what is the status of the storage. Anyone can install standalone system, anyone can charge the system, discharge the system, they can install a storage system as a whole. They can sell part capacity to different discoms, they can use themselves. So it is all use options have been let open, and this activity has been delicensed. So the market or the regulatory setup has been created so that people can easily install energy storage systems. And like solar, in initial years the tariff was around 15 to 18 rupees, and now it has come to 2 years. So similar kind of trajectory is expected for battery energy storage. So I think we are at right now we are in a place where solar was around 8 years back. So government is pushing with uh, storage obligation, trying to make initial traffic with obligations. So government has notified storage obligation wherein each discom is required to meet 1% of its energy requirement through storage. So whether it is solar or wind, that you have to supply through storage, and that is going to increase annually, and it is going to around 24 to 4% by around 29-30. So with this initial traction of for storage will be there, although it is not economically viable or attractable as of now. And other support mechanisms has also been there, like a waiver of ISTS charges for systems with wherein you have battery energy storage systems, and new guidelines for procurement and utilization of battery energy storage systems. Standard guidelines have been notified, so any discom that is looking to hire storage services, they can use that template and float a tender. uh, then CRC has also made provisions for ancillary market, wherein energy storage can also participate in ancillary market. The PLI scheme for battery energy storage for battery manufacturing has been awarded, wherein 50 gigawatt hour capacity is awarded. So I think that has gone to Reliance and Ola and Rajesh Exports. So there are plans of building hundreds of gigawatt hours of battery capacity. And there is also work going on to bring a dedicated PLI scheme, wherein the batteries that are manufactured in those schemes, that will go only for the stationary storage and not for the EV market. So these are some of the tenders that are there as of now. So it's just to give a glimpse that energy storage market is now becoming a reality. So till now there were a lot of talks, but things were not happening on the ground. But since last 1 year, things have started on the ground. In fact, SECI had issued a tender of 500 megawatt and 1000 megawatt hour, and that has gone to JSW, and we had also issued a tender of around 3000 megawatt hour that has gone to Greenco. And but there are certain challenges also with these, as the demand picks up, as the requirement picks up, the resources or the key metals that are there driving these chemistries are limited. So this is a projection for 2030, that by 2030 around 36% of the lithium reserves that are identified as of now, but as we heard that there are new reserves being identified. So unless that happens, so around 36% of lithium reserves are going to be used by 2030, and by 2070 they may be falling short. So similar is the case with other metals also. And the supply chain or the processing chain is very centralized, or is very concentrated. So you can see the raw material supply is mainly there in China. It is there in China, it is there in Chile. But if you see the processing part, it is most of it, most of this is concentrated in China. So that is another challenge in I think. So these are some of the challenges. The main challenge is that cost of storage is very high, so it is not commercially viable as of now, considering the low cost of energy that is there in our Indian EV, in Indian market. So for to meet that, we'll need financial support. We'll need from the government. there are limited market mechanisms, like in other countries there are time of day tariff, where the tariff during the days or during the high peak demand is high, and during the when the energy supply is more, then there is maybe zero tariff, negative tariff, or very low tariff. So they can there are people who can install energy storage system and charge their system during the low tariff and then sell off during the high tariff. So those kind of mechanisms are not there in our market, so which is limiting the installation of energy storage. Then there is demand and supply gap. The demand is huge, and it is going to be even more huge, and that is in fact being most of that is going to EV. So for stationary storage, that demand and supply gap is there. Raw materials are limited, taxes and duties are huge as of now, although the government has taken note of that and there are works on reducing those taxes and duties. Then recycle and reuse, as sir had said that lead acid, we are fully sufficient of recycling almost 90, or I would say 95-98% of the batteries that we are using. That is not the case with other batteries. So we have to think of we have to invest on recycling technologies, and also think on reusing, we can use EV batteries for stationary storage. So some kind of mechanism and industry has to come in between, where the discarded batteries can be made usable for the stationary storage. Then manpower is going to be a big concern. This industry is new for us, and there is a lot of shortage in this kind of market, and it requires very skilled labor and very skilled manpower. So we need to invest in that also. And safety is a very big concern for lithium ion batteries, as we've all seen EV fires. So we'll need standards and quality control for that. Thank you.